Hello and welcome to Math with Mr Amison. Today I'm going to be talking to you about lines of symmetry. To start off, take a look at these. How many lines of symmetry do you think each of these shapes have? Take your time to pause this now and have a think about it if you need to. So if we look at the square first, we have these lines here. They mean each side is the same length. The lines mean, because there's one line on each one, it means each of these sides are the same length. And then we have right angles in each corner. So we have a line of symmetry vertically like this because either side is identical. We have one horizontally, similar with the top and the bottom here. We also have lines of symmetry in the diagonal, where you can see that each side is a mirror image of the other. So in total, we have 4 lines of symmetry. And once you've drawn these, if you count the number of times where these lines exit the shape, there's 8 of them. If you halve that tells you the total number of lines, because each line is counted twice if you count around the outside. So if you ever struggle to count the number of lines of symmetry on a shape, just count how many times the lines exit the shape and divide that by 2, and you've got the total number of lines of symmetry. Now for the rectangle. These are the obvious lines of symmetry, where you have the top and the bottom the same for this horizontal line, and the left and right the same for this vertical line, cutting the shape in half in both directions. This is often a line of symmetry that people assume is correct. However, this is not a line of symmetry. If I take my triangle on this side and then do a mirror image along that line of symmetry, I end up with this triangle here. You can see that doesn't match up with the rectangle. The short side here has to match up with the short side on the other side, and the angles either side of the line of symmetry need to be the same. Which means that this line of symmetry is false. This angle here is different to this angle here, therefore this couldn't be a line of symmetry, and this side length is different to this side length, so that also means it couldn't be a line of symmetry. It's actually a rotation to go from this shape to this shape, and a rotation is different to a reflection. Lines of symmetry occur when we have reflections, not rotations. In a similar way, this line is also not a line of symmetry. Therefore, in this case, we only have the 2 lines of symmetry. For the right angle triangle, we have a line of symmetry from the right angle up 45 degrees to the center of this base here. Because we have this line the same length as this line, and we have 45 degrees either side of the right angle, and we have this line here on the triangle and this line here on the triangle being the same length as well. This, however, would not be a line of symmetry. We may split the angle in half if we choose to, by having the same angle either side, and it may be that we cut this length in half, but we have a different angle here and here, and we have a different side length here and here. So we have to bear that in mind when it comes to drawing lines of symmetry. So this shape only has the 1 line of symmetry. So how many lines of symmetry has each of the above shapes? You can pause and have a think about it if you wish. So for the first shape, the yellow regular pentagon, we can draw lines of symmetry from corner to the middle, the bisector of this opposite side length here, and you can see that this angle and this angle are the same, these side lengths are the same. We've got an exact mirror image of the shape either side, and we can do that from each of the 5 corners, and therefore we have 5 lines of symmetry. The black regular octagon, the point here is it's regular. If these were not regular, you couldn't necessarily do this, and we'll talk about that in a minute. For the octagon, In a similar way, we can go from the middle of this line to the middle of this line to make a line of symmetry where it's exactly the same on either side. And we can do that in the middle of any of the sides. We could also draw a line of symmetry going from one corner to another corner, to its opposite corner. Not any corner, has to be its opposite corner, to make exactly the same both sides. And we can do that with each of the other corners as well, which gives us a total of 8 lines of symmetry in a regular octagon. So 5 lines of symmetry in a regular 5-sided shape, 8 lines of symmetry in a regular 8-sided shape. You can see where that's going. In this scalene triangle, we cannot have a line of symmetry because no matter where we drew it, the angle would be different on either side of this line of symmetry, or the side lengths would be different on either side, or both. So if I drew a line, if I split this side length in half and then split the angle in half, it would look nothing like it on the other side. The side lengths would be different, the angles would be different. It just doesn't work. You can't split this angle in half because it wouldn't cut this base length here in half either. So there's no lines of symmetry on this shape. You can pause to have a think about this question as well. How many lines of symmetry has each shape? So here you can see that the top 2 lengths are the same, and down here the bottom 3 lengths of this pentagon are the same. It's not a regular shape. Well, you can see we can draw a line of symmetry down the middle because these side lengths are the same, the angles are the same either side, these are the same. This has been split in half, the angles are the same either side of the line of symmetry. It just works. And these angles here are the same as well. Everything about it is correct. However, we can't do that for other sides. If we did this, this top length is a different length to this length here. While it may look like the angles might be the same, they're probably not. If you have a look closely, they're not quite the same. Similar with this this supposed line of symmetry here, it's exactly the same, just on the other side. And this one, yes, we've got the same side length either side here, and we're splitting this length in half, but you can see that this side length here is different to this side length here, and you can see that the angles either side of the line of symmetry here are different. So this line of symmetry doesn't work either. It's not a real line of symmetry. So it only has, similar for this one, so it only has one correct line of symmetry, this irregular pentagon. For B, we could try drawing lines of symmetry diagonally, but you can see that that's not a right angle, so these aren't the same. I could draw it the other way, but you could also see that these angles aren't the same. So diagonal lines of symmetry aren't there. But then I could draw vertically, and you can see it's just not right. If I split these side lengths in half, the angles are different. Even if this was in half and the angles were the same, it just doesn't work. So this one didn't have any lines of symmetry. For C, we can cut the shape in half vertically with a line of symmetry because the angles are the same on either side. You can see it's a good mirror image. The angles are the same either side here, the side lengths are the same here, the same up here, angles are the same, side lengths are the same, and it works well. If we try to do this horizontally, it also works, where we have these angles the same as these two. You can see it's a good mirror image, 90 degrees either side of the line of symmetry, same side lengths either side of the line of symmetry. If we try and do this diagonally, you can see straight away these angles are different. It's not going to work. And you can actually see that this shape here is a rotation of this shape here, therefore it's not symmetrical down that line. As we talked about before, rotation is different to symmetry. Similar for that diagonal there. So we only have those two lines of symmetry for this shape. So Jakob says the following: this right angle triangle has one line of symmetry. This proves that all right angle triangles have one line of symmetry. Explain why Jakob is wrong. You can pause to have a go at it. Okay, so if you want to know why Jakob is wrong, the easiest thing to do is to draw another right angle triangle that's not isosceles like this. And you can see if we try to draw a line of symmetry down here, then the angle either side is different. The side length here is different to the side length here. And we've proved that is not a line of symmetry. And we've already shown that no matter which corner we go from now, that the length either side of the line of symmetry is going to be different. Therefore, we can't do a line of symmetry in this right angle triangle at all. It actually has no lines of symmetry. So, have a go at these questions. You can pause to have a think about them. And you can have a go at sketching the diagrams if you wish. You could have a go at just thinking about it, where you might shade in triangles or squares to answer these questions. I'll go through the answers in just a second. So, for the first one, for one line of symmetry, we could have placed our triangle here, or here, or here, and those three answers represent the lines of symmetry going in the different directions. A vertical from this point to the vertex here, and from the center of this line to the vertex here for the last one. For three lines of symmetry, shading in the fewest possible extra triangles, we'd have to shade in all of these to go from this point to here, this point to here, and this point to here. For this shape here, one line of symmetry, by shading in one extra square, we could have had this for a vertical line of symmetry, this for a horizontal line of symmetry, this for a diagonal line of symmetry from top right to bottom left, this for diagonal from top left to bottom right. For two lines of symmetry, by shading three extra squares, we could have had this for a horizontal line, or this for horizontal and vertical line of symmetry, and this for diagonal lines of symmetry from top left to bottom right and top right to bottom left. For four lines of symmetry, it needs all four, both diagonals, horizontal and vertical. So we need to shade in these 7 squares, 2 at the bottom, 2 at the top, 1 here and 2 here. And for the final question, if you want to shade in exactly 3 more squares so that there's only one shaded square in each column or row, so each column is the vertical, up and down, each row is the horizontal, left and right, so 1 in each of those columns and rows, so that it has exactly one line of symmetry. You can do that like so. Wait, no, that actually doesn't work. If you have a think about it, this doesn't work because we can have a diagonal line of symmetry along here, and we can have a diagonal line of symmetry down here. So this actually has 2 lines of symmetry. And it's useful to point out that in questions like this, it's difficult to always get things right first time, and it's okay to make a mistake. So I would like you to have a think about how you might do this in a way where you have one line of symmetry. This does have 1 square in each row or column. Can you change the answer so that it has exactly 1 line of symmetry? So to finish off, this shape is made up of 9 identical equilateral triangles. Can you shade in exactly 1 of the tiles so that the overall shape has no lines of symmetry? Have a think about that. I'll leave it with you, and thanks for watching, and see you next time. Have a good day.